On a modern construction site, massive earth-moving equipment and human workers operate in constant, overlapping proximity. A hazard can materialize in a fraction of a second. Every year, preventable site hazards lead to life-altering injuries. Here in Aotearoa, New Zealand, the team at Shiny Data Technology set a clear target: apply advanced computer vision to ensure every worker goes home safely at the end of the shift. Traditional safety oversight relies on manual site audits, but a human safety director managing hundreds of subcontractors and multi-story scaffolding simply cannot monitor every blind spot simultaneously. The industry attempted to automate this surveillance using centralized, cloud-based vision language models. Plumbed directly into CCTV feeds, these massive AI systems were tasked with interpreting live site conditions. The deployment failed. Standard cloud computer vision pipelines lack the mathematical rigor and processing speed required for physical hazard detection. Delegating high-consequence safety monitoring to an imprecise system leads directly to physical casualties on the job site. Consider the mechanical speed of a multi-ton excavator pivoting on its axis. Intervening in a fatal near-miss requires instantaneous reaction times. Raw vision language models fail on multiple fronts. First, they hallucinate fine details in cluttered environments, guessing if harnesses are latched. Second, they lack spatial reasoning, generating false 3D distance calculations from flat pixels. Finally, centralized cloud transmission induces severe 920 millisecond latency and astronomical API costs. In a fast-moving construction zone, a 920 millisecond processing delay is a lethal blind spot. Visual intelligence does not equal spatial intelligence. Securing a physical job site requires deterministic precision. To eliminate that delay, the initial analysis must leave the cloud and move to the physical edge of the network. Shiny Data Technology engineered Construction Safety AI. It is a two-stage, detection-guided architecture that anchors the reasoning power of the cloud with local spatial mathematics. Stage 1 deploys an optimized YOLO V11N model directly on local edge devices. Operating locally, it identifies workers and machinery in under 2.5 milliseconds. These coordinates feed into Stage 2, the spatial relationship engine, calculating distances between entities as a strict percentage of the image diagonal. It takes those hard geometric coordinates and translates them into structured natural language, explicitly stating that a specific worker is directly adjacent to an excavator. Grounding the AI in locally verified deterministic pixels completely removes spatial guesswork from the equation. That structured text conditions the Azure GPT-4o model. Instead of guessing, we force its visual attention to verified coordinates, eliminating hallucinations of non-existent PPE. Finally, Stage 4 secures the output. The text response passes through a 3-tier regex parsing engine. Large language models can drift in their response formats over time. These fallback layers extract the exact hazard data, guaranteeing final compliance logs remain perfectly structured. A safety supervisor sees the result immediately. The simulator dashboard highlights infractions in real time, matching localized bounding boxes with severity-coded OSHA compliance recommendations. This pipeline does not politely ask a model if the site looks safe. It forces the architecture to mathematically prove its compliance assessment. A single static image only tells part of the story. Construction threats evolve over continuous minutes of ongoing site activity. To address this, Construction Safety AI deploys a temporal hazard aggregator capable of parsing large 500 megabyte video files through customizable frame sampling policies. As the video runs, the system clusters repeated hazard warnings. It calculates the exact incident duration, logging the first and last timestamps to definitively report whether a threat resolves naturally, persists, or escalates. Site auditors review this data through a chronological timeline. Instead of scrubbing through blank footage, they expand specific panels to view moments of highest threat. A brief spatial violation is a warning. A persistent, clustered violation is a crisis. The temporal aggregator differentiates the two automatically. This chart compares hazard detection accuracy. A raw VLM produces an F1 score of 0.65. With our two-stage pipeline, accuracy jumps to 0.94. On this second chart, the massive 920 millisecond cloud delay is bypassed by a 2.4 millisecond YOLO edge inference. This combination of extreme precision and near-zero latency allows for 100% automated OSHA compliance parsing in real time. This architectural shift provides the absolute reliability required for autonomous, real-time safety intervention on the physical job site. Deploying edge computing serves a critical sustainability function. Processing the bulk of visual data locally drastically reduces systemic energy burn in centralized cloud GPUs. It enforces privacy by design. Raw video feeds are analyzed on-site. Only lightweight, structured text descriptions are ever transmitted to the cloud. The platform is built for production scale. Packaged in slim Docker containers, the deployment is fully automated via Google Cloud Build and Cloud Run scripts, ready for global application. Most importantly, it relies on a human-in-the-loop governance model. The AI functions as a high-speed filtration shield, equipping human safety managers with exact data rather than replacing their final oversight. For the Aotearoa AI Awards, Shiny Data Technology presents a market-ready solution built to protect human lives locally and internationally. AI innovation demands the integration of engineering rigor, responsibility, and safety into the very fabric of the physical world.